All right, guys, this is the eye, part one, because I'm sure there's going to be two parts. So, when it comes to our senses, we'll start out with the eye first, but our senses all take in energy from different sources, right? So, like, the eye takes in light waves. And so, to talk about light waves, we have to talk about the electromagnetic energy spectrum, right? That includes like X-rays, radar, radio waves, and light waves. And there's a really small section on it that lets us have the ability to see colors, right? The color spectrum right there. It's very, very small, but these are the ones that our eyes are able to pick up on and transform into colors. So depending on what species we are, we have different ability to see different scales of light, or even being able to see different types of waves, right? So I guess this is a nice comparison between dogs and humans. They obviously can't see a lot of the colors that we can. Just shows there's a lot of diversity on who can see what. Now, words we're going to talk about a lot are amplitude and wavelength when it comes to the eye and the ear. So when it comes to wavelength, that's going to be over on the left here, right? So it's going to be this side over here. And so when it comes to how we perceive color, the shorter the wavelength, it's more like a blue color. So on the Roy G. Biv scale, this is the Biv is over there, the blue, indigo, violet. And then on the longer wavelengths, that's the Roy part, the red. Red would be the longest wave. When we talk about wavelengths, it means how far apart are the peaks of two waves. If the two peaks are relatively close, you're going to get a blue or a purple color. If the wave peaks are very, very far apart, the wavelengths are long, it just means that you'll have more of a reddish color. Now, amplitude is how tall or short are these waves, right? It's not anything to do with the space between. It's how tall or how maybe short they are. The taller the wave, when it comes to the vision, it's the brighter the color, and then the shorter the wave, the duller the color, okay? So if we look at wavelength, this is going to be what hue, right? The color. Wavelength determines the color, and remember, further apart is red, closer together wavelengths are going to be blues and purples. And so with our ability to see colors here, we have Roy G. Biv coming back, and based on all the different color mixing with light and how it works, our ability to see these 7 colors, when you mix them, it lets us actually see like 7 million separate hues. So that's why all blues don't look the same. There's variation between them, right? There's so many different colors we have the ability to see. Now, we will probably watch this clip during our Zoom meeting because if I record it on here, it won't let you hear the sound. So with this, we'll talk about how men and women actually have the ability to see different ranges of colors. All right. So amplitude, like we talked about, the intensity of the color. Taller is more intense versus shorter is more dull. Oh, so we'll go back to that one last time. Bright yellow versus a very dull, tame green. Now, anatomy of the eye is super important. That's why you guys had to fill out the eye worksheet, and then you have a quiz over structures and functions today, because it's something that you do need to know, especially for our upcoming test. So all of these words, no way. That is way too many. We're going to go over the parts that you need to know for AP Psych. This is not full-on anatomy class. So we'll start from the front of the eye and work our way back. So the first part of your eye is your cornea. Don't do it, but you could hypothetically, or if you wear contacts, you probably touch it every single day. It'd be the part of your eye that you can touch with your finger. It's this clear bulge that pops out from where your eye is, right? And its job is 1, protection, 2, it's the place where light starts being bent and focused for the first time, right? So when anything enters your eye, the cornea is the first thing that's like going to shift the light into a different shape so it enters your eye the correct way and goes towards the pupil. Another thing is it's protection. So if you've ever gotten anything on your eye, or if you've ever scratched your cornea, it hurts really, really bad. Anytime we have anything in our eyes, we know, we're aware of it and we want to get it out because it's really, really painful. Your cornea has a ton of pain receptors on it. And that's because your eyes are so important to you that we need to be very aware if anything's in there possibly going to lead to damage. So our cornea is shaped to have this many pain receptors up as a protective measure. So the next thing we can look at is going to be our iris. It's just the colored part of your eye, and it's actually a muscle that changes shape depending on how much light your eye needs to have a clear view of something. Right now I'm in a really bright room, so I probably have very large irises and very tiny pupils. The muscles have all like expanded because I don't need a lot of light being let in because there's so much of it. Because there's so much light in my space, everything is very clear and I can easily pick up on it. Versus if I were to all of a sudden go and walk in the back room that's really dark, my irises would have to get really small, because when the iris gets smaller and thinner, the pupil becomes bigger and that lets in more light. I need more light in to help my eyes function and me to be allowed to see anything or able to see anything. So that's the iris's job. It's this muscle that contracts and expands depending on how much light my eyes need to function. And then we have the pupil, which is actually just an opening, right? It's a hole in our eye, basically. That's why it looks dark. And in this hole, that's where the light floods in. And then eventually will go in and hit the back of your eyeball, your retina, so you can start seeing things, right? So our pupil has to be able to open or shrink, right? Depending on how much light is needed. And this will make more sense when we talk about the rods and cones, because your eye needs an excessive amount of light in some degree to be able to process vision, and your pupil's job is to regulate that. And your pupil, it can't make itself bigger or smaller. Your brain will give the iris the signal to do that. The pupil's just a hole. It just sits there. It really doesn't have any ability to function on its own. It's a hole. That's it. All right. And then if we go behind where the iris is and behind the pupil, you're going to have the lens. It's actually like, kind of think of it like almost like a contact lens that's permanently in your eye. And it's transparent, it's see-through as long as you're healthy. People would have cataracts, if you've ever seen that, or animals get cataracts a lot when they get old, and their eye looks foggy, their pupil does, and that's because their lens is actually foggy. That's the part you're seeing. In a healthy person, it's super transparent, and it has the ability to get thin or to get thicker. It just depends on what you're trying to focus on. So if you want to mess with your lens right now, put your finger out way, way far in front of your face, way far away. And that way your lens is going to be actually like super, super thin. It's stretched out. It's pretty flat. But if you bring your finger closer and closer to your eye, just one of your eyes, it doesn't have to be both. You can just close one of your eyes and do it back and forth. You can feel your lens getting thicker, because it has to change shape to focus in on your finger when it gets closer and closer to your eye. So your lens is changing. Now, as we get older, just like our bodies typically become less flexible, so does our lens. And if our lens has the inability to stretch, thin, fatten, do all these different moves to get you to focus on something, what happens is you have to get glasses, because if your lens is faulty and not doing what it's supposed to be doing, then you may need glasses to correct it and kind of like act as an additional filter for light to bend through. All right, now this whole idea of what I made you do with your lens, the thinning and the thickening, going back and forth and back and forth, that's called accommodation, right? The fact that your lens can do that, it's accommodating you. It's helping you, and it's changing shape as needed. So if you ever see a word about accommodation, it refers to the lens's ability to change shape to accommodate to what you need, to help you to switch its shape and size and thickness. Now, people who are nearsighted versus farsighted, it could be because their lens is not doing its job correctly. It also could be because their eyeball has a different shape to it. So people who are nearsighted, closer objects are seen clearly. That's why nearsighted, they have the ability to see things near, but distant things are blurry. It could be because their lens is misfocusing the light and it's just falling short of the retina. This candle right here should be back on the very, very back of the retina. It's not quite making it. So this is where the crisp, clear picture is, and back here it'd be like blurry. It also could be because your eyeball is just like elongated a little bit more than what a typical eyeball would be, right? And it could make sure that your lens is doing the job correctly if you had a regular eyeball, but because it's a little longer, it's still not reaching the back. Farsighted is just the opposite. People can see far away. They can't see things that are near, and it's because their retina is either too short or their lens is faulty, and it's pushing it way back here when it actually needs to be here. And so because of that, this image is still blurry because here's where it actually gets all focused. Now the retina is the whole back part of the eye, right? So this is like, you can see the pupil back there, but this is the whole back of the eye. The retina is the entire wall. So usually on these drawings, if we have like the cornea and the pupil and stuff in the lens, this whole back wall back here is going to be our retina. And the retina is where that fancy word transduction comes into play. This is where you have all these sensory cells that let you absorb the light and transduce it or translate it into a neural impulse. So when an image goes through your eyeball, through the cornea, through the lens, what actually happens is the picture gets flipped upside down and backwards, and then it's put on the back of your retina that way. So everything that you see right now, if you're looking at me, if I were to take a picture of what is on your actual retina, I would be upside down and backwards. Okay? That's what your eyes actually are being processing when they have these images shifted on them. But your brain flips them right side up, and that's how we perceive the world. That's why we don't see everything upside down and backwards. So this whole wall back here is the retina. This is shown on the retina, right? That's where this upside down backwards candle is. Now in the retina, you do need to know the different cells that make it up. So you have the receptor cells that are probably the most important part of the retina are the rods and cones. Receptor cells are the ones that transduce information. Transduce is like a fancy word for translation. It takes the energy waves, so the light waves we see. So honestly, when a picture is coming to your eye, the colors and stuff and the shapes, you have these waves coming in and being sucked into your eyeball. And when it goes and hits the back wall, these rods and cones translate it to a neural impulse. They change it to brain language. Brains don't understand light energy. These guys have to transduce or translate it to a neural impulse. So here's your fancy transduction term. I know it's a weird one. It just means transferring of an incoming stimuli into a neural impulse. So whether it be light energy, sound energy, physical energy like touch, or a chemical energy like through smell and taste, we just have to transfer it or transduce it or translate it to brain language. So rods and cones. Rods mostly in the peripheral or periphery or sides of the retina, and they see things like black, white, gray, shapes and outlines. They're what lets us see it like twilight or dark, right? So if I shut off all the lights right now in your house and shut all your curtains so it'd be really dark, the reason you can make out shapes and stuff, and maybe not great color, but shapes, is because your rods. Now your cones are more centrally located or in the fovea that we'll talk about, and they see colors and details. So the fovea is going to be the part where cones are most densely compacted, but we have far more rods than cones in our eyes. So you don't need to know the numbers, but yeah, definitely more rods. Cones are not activated unless we have light coming into our eye. That's why the pupil can get bigger to try to suck in as much light as possible. Now the fovea, if this is the whole back of the retina, the fovea is right in the middle part of the retina, right above where the optic nerve leaves the eye. And this is a densely compacted area of cones. And so it offers visual acuity. Acuity means like highest amount of detail. It's very accurate. That's what I think. Acuity sounds like accuracy. And so when I am looking at this stuff, my fovea is there with all these cones that pick up color and detail. So that's why when I want to look at something, I look at it dead on. If I want to see the details of something, I don't like look at it out of the peripheral of my eye. I pick it up by looking directly at it. Our peripherals don't pick up much color, right? If something were to come up on the side of you, things have to be pretty far in front of your face before your rods even say, oh, hey, I see something. And you don't get to see the colors until you're far enough forward that your cones are activated. And so our fovea is just where they're densely compacted. All right, so I'm going to pause there for this one, and then we will pick up the rest of the anatomy on part 2 of this. All right.